Hello students, welcome to the Advanced Materials Advanced Manufacturing Laboratory. We are located at the Technology Center ASU Polytechnic campus. Today, we are going to take you on a virtual tour of our laboratory and show you the laboratory needs and the instruments we use on a daily basis and what they're used for. In our lab, we study the interactions between nanoparticles and polymers specifically for additive manufacturing. In my hand, you can see a sensor which is volatile organic solvent sensor we 3D printed in our lab. Today, we'll show you the complete procedure of 3D printing a volatile organic solvent sensor, which consists different type of organic solvents. The first thing we do as soon as we enter the lab is to take our lab coat, a safety goggle, and a pair of gloves of our size. As you can see, one of my colleagues is working on a complicated instrument called rheometer. So, he'll explain you what will we do with it.
Rheology is used to describe and assess the deformation and flow behavior of materials. Flow is flow at different speed, and solid can be deformed to a certain extent. Oil, honey, shampoo, and hand cream, they all behave differently in terms of their physical behavior. They can be put in an order. On the one side is liquid, and on the other side is highly viscous, semi-solid substances. Rheology measurement is important for many applications. For instance, when the viscosity of human blood is high, it usually indicates the cause of abnormal shaped red blood cell, such as sickle cell anemia. Rheology is also essential in terms of material manufacturability and can be used to study the phenomena such as particle jamming during 3D printing. So to run a rheology test, the first thing is to program your experimental steps on a provided software. We will need to set up the shear rate and the temperature and points per decay. And then today I have two different types of samples with different viscosity. As you can see, this one has a liquid-like property, while this one has a more solid flowability. So we will test both and compare their rheological behavior.
First, we will load the samples between the parallel plates. And during this step, make sure there's no bubbles trapped in between the plates. Okay. And then we will lower this top plate at 100 micrometer gap. And once the gap is totally filled with the material and reaches 100 micrometer gap, we will trim off the excess material so that they won't affect the testing result. So now we can start the test. And as you can see here, the top plate will rotate from a small shear rate from about 0.1 to 1000. So here's the result. As you can see, the highlighted line is for the more solid-like material. It has a much higher viscosity comparing to the more diluted polymer solution. So this would help us to study the processability of these two kinds of material during 3D printing.
So here we have thermogravimetric analysis equipment. So what this machine does is it will analyze what composition you have for each nanoparticle polymer composite. So we'll first load the sample onto this pen here, and then we will load this pen. So how this machine works is it will increase the temperature of this sample up to 1000 degrees Celsius, and at the same time it will measure any weight difference. So if you have a material of one polymer, one metal at different temperatures, at a lower temperature the polymer will first degrade, and then the weight you measured will be the amount of metals you have. In that way, we will know the exact composition of this sample. So right now we will close the furnace here and then fill the chamber with nitrogen and start our experiment up to 1000 degrees. The test has finished and the furnace gradually lowers. Right now it's pretty hot. But you can see that most of the material there is already evaporated, leaving some trace of metals, which we can use to determine the composition, the weight percentage of the metal particles inside the composites.
Hi guys, this is a DSC instrument. It's a differential scanning calorimetry instrument. It is used to determine the thermal phase transitions takes place in a polymer. So for that, we heat the polymer sample as well as the reference sample together to maintain the constant temperature throughout the test. So in some cases, polymer undergoes exothermic or endothermic reactions. So depending on that, we need to increase or decrease the temperature with the addition or subtraction. So that heat flow versus temperature, or the thermal transitions versus with respect to temperature, is determined from this instrument.
Sample preparation is a very critical step to obtain an accurate DSC measurements. So in this case, using a tweezer, we place the pan in the blue T0 hermetic lower die, and then we place the sample having approximately less than 10 milligram weight into the pan. Press down the handle of the T0 press to seal the pan and lid together. Then place the sealed DSC pan in the desired pan location inside the heating chamber. There are two thermocouples, one is for sample pan and one is for reference pan. Then we close the chamber with the lid and we start the procedure. After loading the sample in the chamber, we feed in the information about the sample like material, weight, and the heating cycle like the heating rate up to the heating temperature in the software, and then we run the program. Differential scanning calorimetry can be used to measure a number of characteristics properties of polymeric sample. Using this technique, it is possible to observe melting, crystallization, glass transition, as well as the study of oxidation and other chemical reaction takes place in material as a function of temperature.
3D printing or additive manufacturing is the construction of a three-dimensional object from a digital 3D model. It was invented in 1970s. The printing efficiency and the resolution are still developing. In 3D printing, the nozzle and the printing bed are controlled by a computer, with materials being added layer by layer.
This printer can do extrusion-based printing, meaning it can print polymer melts from a heated nozzle or polymer solution from a syringe. We first edit a digital model with the computer, then import the file into the device, telling it what to do.
So here we have a solution of nanoparticles, and it's a 3D printed substrate which having a microchannels. So this solution will be deposited into the microchannels through capillary action.
We start by preparing a 10 mg per ml solution of MXene particles in ethanol, and using a micropipette, we deposit 2 microliters of this solution into the reservoir of the substrate. After that, we can see that this solution gets sucked into the microchannels via capillary effect and gets evenly distributed into the microchannels. Once the ethanol evaporates, we get thin single-layer structures of MXene flakes deposited into the microchannels. We can repeat this step to get multiple layers of MXene as per our requirement and the properties desired.
This is a homemade setup for volatile organic compound gas sensing. So in this, it has a solution of methanol which we bubble through a specific flow rate depending upon the concentration of molecule required. So this VOC molecules are directed toward the sensor. When the VOC molecules get adsorbed on the surface of the sensor, it increases its total resistance, which is recorded here with a multimeter. So that gives us the response to that concentration of methanol vapors. So this is due to the obstruction to the electron flow due to the absorption of the foreign molecules.